we have with us Ravi Pandya, who is a PhD candidate at the Robotics Institute in Carnegie Mellon University. Ravi is advised by Changliu Liu and Andrea Bajcsy. His work is at the intersection of safe control, robot learning, and human modeling, focusing specifically on enabling AI and robots to understand the influence they have on people in order to stay safe while interacting with humans. Ravi is a recipient of the National Science Foundation Graduate Research Fellowship. And prior to his PhD, he was a data scientist at Ericsson working on multi-agent reinforcement learning. He received a BS in electrical engineering and computer science from UC Berkeley in 2019. And today, Ravi's talk is going to be about influence-aware safety for human-robot interaction. I'm super excited to host Ravi here, and I'm going to stop sharing my screen. Ravi, please feel free to take it away.
Cool. Yeah, thank you so much for having me today. I'm also excited to share my work and hear about what people think. All right. Yeah, so I'll be talking about my work on influence-aware safety for human-robot interaction. And I'll just start by mentioning that people are already interacting with AI and robots all the time, from chatbots to recommendation systems, autonomous cars, and robot vacuums. There's robots like an AI interacting with people all around the world. And maybe some of you have heard about this, but a few weeks ago, people were starting to talk about how ChatGPT was actually kind of being super, what they were saying, sycophantic or like very overly agreeable. So I wanted to pull out a few quotes about what people were saying about how it was acting. So one woman was saying that her husband was talking to ChatGPT all the time, and it was teaching him how to talk to God, sometimes that the bot was God or sometimes that he was God. People on Reddit have shared stories like this person saying their partner was talking to ChatGPT and it was talking to him as if he was the next Messiah. And people have found that it's actually like pretty easy to get ChatGPT to respond like this. You basically just have to convince it that you feel like a prophet, and it's like, yeah, you're right. I think you're a prophet, and like you feel something super real. And this actually culminated a few weeks ago in OpenAI releasing this report talking about sycophancy in GPT-4o. And they said that they're rolling back this update that they made because they had tuned the model so much to focus on short-term feedback to the point where it felt overly supportive but disingenuous. And like it's pretty obvious, like all of us sort of feel like, chatbots shouldn't be acting like this. But the question I want to focus on is like, why does this feel weird? And I pose that the reason that this feels strange is because the like AI is influencing people in a way that is like negatively impactful, specifically that the behavior of the AI could ultimately cause real world harm, either to the person that's using the system or to other people. And we've already seen some examples of the potential negative impacts of AI influencing people through like political polarization or like taking dangerous actions after interactions with chatbots. But I'm not here to say that all influence is bad. Oftentimes, chatbots can be super useful. Like they can give you super useful information, convince you of like interesting things to learn about. And also in embodied settings, influence may actually be necessary to complete a task. So in this video on the right, you can see an autonomous car merging through multiple lanes, and it really wouldn't be able to do this if it wasn't able to influence the other cars around it to like slow down and make room for it. So the pitch in this talk is essentially that robots need to influence people carefully by understanding the real world downstream outcomes. They can influence people while keeping them safe. And I formalize this idea in my work through the influence-aware safe control problem, where we're explicit about what safety and influence mean while learning robot policies. And I'll step through this problem formulation a bit now. First, there's the robot's objective, meaning maybe it wants to pick up some blocks on this table, and it's subject to the physical dynamics of the system, and also has some safety constraint, like maybe it wants to keep its end effector from colliding with the table. And people have done this a lot in regimes where you want to just avoid collisions or guarantee that robots won't fall over while they're walking, stuff like that. And people have also included a human inside this loop, which means that you now include the human's control inside the physical dynamics, and the safety constraint is with respect to this person. And in recent years, people have also done work where you're modeling the person as a goal-reaching agent, where they have some objective in their mind, and the robot needs to stay safe with respect to that model as well. And on the other side, not thinking about safety, there's been some work on interacting with people while considering how their intentions are being influenced by the robot. And this is often treated as a problem of learning the dynamics of some like latent intention of the other agent. But there's actually not too much work that's trying to do both of these things together, where you want to do safe control under these additional dynamics, where the human's internal state is affected by the robot's policy. So in my work, I'm aiming to address this full influence-aware safe control problem. And one question is like, why is this formulation interesting? I've given some motivation up front, but really the key piece of it is that the intentions of other agents will affect how safe you can be. So for example, if you're super confident that the robot can change the person's intention, then the robot might be able to be less conservative around them. But on the other side, you need to be sure that the robot's not overconfident in its prediction to the point of becoming unsafe around people. So a lot of my work falls into one of these two buckets, either safe control with human models or influence-aware human-robot interaction. But I also have some work at the intersection thinking about the full influence-aware safe control problem. And in this talk, I'll talk about some work in each of these buckets. So one question you might have is why we're posing this as a safety problem, and specifically, like, why do we need safety at all? Like, can't we just tell our robots, don't collide with people, don't do unsafe things? And let's take some motivation in the form of this video in an embodied setting. So here we see a biker going pretty fast through this forest. And there comes a point where it looks like if they go on their current trajectory, they will collide with this tree. But of course, there are paths that they could take to avoid collision. And you can see that they ultimately choose to steer left. But let's rewind a bit to this moment here. The question is like, why did the biker need to take this decision on which way to steer so early relative to when they were actually going to collide? And the answer is about considering the dynamics of the system. And this is one major reason why safe control is non-trivial. So you really have to understand that if the bike is already moving at some speed, when you get sufficiently close to the tree, there's nothing you can do to avoid collisions. And this also gets even harder if there's uncertainty in the system, like if you don't exactly know where your obstacles are, things that you thought were safe might become unsafe in the future. And this is additionally complicated by potentially having other agents in the scene because you don't necessarily know what they're going to do, so it's even harder to stay safe. So let's look at this simplified example where now we just want to avoid this set of red states, which is called our failure set. If we account for the dynamics of the system, thinking about like if the bike is moving at a particular speed, what are all the states where it's inevitable that it's going to fail? It ends up looking like this set of states, where no matter what you do, if you're sufficiently close, even if you try to steer all the way or try to brake, then there's nothing you can do to avoid collisions here. And this is what's called the inevitable failure set, or the backwards reachable tube of the original set of failure states. So we want to know how we can encode safety mathematically. And we rely on this idea of a value function that can tell you whether the system is safe or unsafe, basically whether the state is inside the inevitable failure set. And we want to ensure that basically no matter what state the system starts in, it'll get safer over time. And this can be thought of as wanting to decrease the system's energy, where the energy is represented by this value function. So starting from some unsafe state, the system might want to move like this towards a safer state over time. And one big question in safe control is, where do we get this magic value function? And this is really the biggest question in safe control. In general, this value function would be synthesized offline for a particular dynamical system. And another question is, how do you actually compute safe controls given this value function? And in some of the work that I'll be talking about soon, we think about a particular version of this where you can create a linear constraint on the controls based on your value function definition. And so this is a pretty straightforward way to construct safe controls given your like existing value function. And now that we have this like foundation for safety, I'll jump into one of my projects where I'll talk about multimodal safe control for human-robot interaction. So in this work, we modify our original problem formulation because we're not ready to jump all the way in yet, to remove the dependence on the robot's control and focus on the case where we have multimodal uncertainty in what the human is going to do, where I mean multimodal like a bimodal probability distribution, not like vision and language. And we'll ground this in a domain where the two agents are trying to reach different goals. There's multiple potential goals here for the human, denoted by Z1, Z2, and the robot has its own goal, denoted by ZR. The robot's trying to keep a belief over the human's true goal since it's not known to the robot a priori. And there's additionally uncertainty because people are not perfectly rational actors, so there's a little bit of noise in the human's dynamics. And this is very naturally modeled as a mixture of Gaussians because we have uncertainty over the discrete mode of the human, which is their goal, and there's uncertainty within each mode from the dynamics. And before we can think about safety, we have to write out the actual systems dynamics, which in this case is the joint human-robot system written down like this. And in this form, F encodes both the human and robots like autonomous dynamics, and G contains only the control terms for the robot's dynamics because the robot's control, which is denoted by UR, does not have direct control over the human. It has this like indirect control based on its own actions. And this is just writing out our Gaussian mixture model distribution for the human. And this also means that we have uncertainty in the F function because we have uncertainty in the human model. So we're going to think about how we can synthesize safe controls in this scenario. And first, we'll assume that we have already synthesized a value function that's valid for all the modes. So for example, with interacting with a person, you say that they have some maximum velocity they could move at, and you've synthesized a valid value function given that assumption. And now, this was our linear control constraint we wanted to satisfy. But because we have uncertainty in the human, we actually can't compute this, or we can't satisfy this constraint directly. So instead, we try to satisfy this chance constraint, which means that the probability that this constraint is satisfied should be greater than or equal to 1 minus epsilon. And the question in this work is, how do we compute a least conservative control that satisfies this constraint? And I specify least conservative here because you can imagine that if we don't know what the robot, or we don't know what the human is going to do, the robot might just run away from the human. But because the robot has its own tasks to do, you don't want to be overly conservative like this. So we can start a bit simpler and have this illustrative example of our method where we get this very simple safety constraint for a particular set of F and G. And we can look at what the space of possible human models are and what control constraints that those impose on our space of robot controls. So on the left, this is our human model space where every point corresponds to a particular constraint in the control space based on this safety constraint. And in general, in safe control, we're given some reference control uref, and we're going to project it down to the closest safe control in our control space for the robot. So back to our example, we had this like normally distributed human model, which means that every point in this space actually gives you a different constraint. And because the support of a Gaussian is unbounded, you end up actually with an infinite number of constraints. So instead, we could go back to our probabilistic constraint and look at only the points that are 1 minus epsilon likely and find the worst case version of this, which gives you a single constraint that satisfies our chance constraint. And you can compute this in general with the simple optimization. But the key point is that now treating it like this, you can take a single point in your model space as the worst case model for the human, and this corresponds to a single constraint for the robot to stay safe with respect to. But we're also interested in the case where there is multiple potential modes of the human model. So this gives you multiple potential constraints. And prior work has thought about just doing this with unimodal uncertainty. So mapping this onto our method, we can think about just picking the most likely mode of the human and staying safe with respect to that. But this might be potentially unsafe if the human's true mode is actually not what we thought it was. Other work has dealt with more general uncertainty by bounding all of the uncertainties into a single ellipsoid, but this might end up being overly conservative. So for a less conservative baseline, we take the intersection of the worst case constraints from all the modes. And in our work, we actually noticed that we have some freedom in choosing the epsilon bound per mode. So because we have this probability that of which mode the system is actually in. So we choose epsilons that balance these modes such that the constraint is identical in the control space. And this is called the multimodal safe set algorithm. And back to our problem formulation, we have this multimodal Gaussian uncertainty over the human, and we run simulations in the setting to compare our constraint balancing approach to these baselines that I just mentioned. And here in our videos, basically the robot is not thinking about its own goal right now, but is just following the human around. And you can see that the human is this blue dot that's moving between its goals, and the robot is the red triangle that's trying to track the human. You can see in the unimodal case, which is the left video, the robot actually ends up colliding with the human, meaning it breaks this minimum safe distance bound anytime that the human changes its mind, because it's not accounting for this possibility. Versus our method on the right actually accounts for this possibility that the human could change, and so stays safe with respect to this model of the human. And you can see at the table up top, when you compare the safety rates of all of these controllers, our controller does satisfy the desired safety rate, but is not overly conservative, which you can see through the control set size, meaning that it's not like overly restricting the set of safe controls for the robot. And you might be thinking, like, maybe this Gaussian mixture model assumption for the human is a little too restrictive to be useful. And I think that's a fair question. But if you look at some recent pedestrian prediction models that have seen some success, if you can zoom into their architecture and see that they're actually predicting a Gaussian mixture model for predicting the human's position in the future. And this is a great sign because it tells us that this multimodal safe control approach is compatible with sort of modern learned models of people. And I haven't actually done this, but the pitch is that you could do this. So now I'll switch gears and talk a little bit about some of the more HRI focused work. And one of the big questions is, where do you actually get influence-aware models like this that kind of sort of model what the person is going to do, conditioned on what the robot wants to do? And the answer for a lot of like self-driving car companies, because they have like models of what other drivers are going to do in the scene, has been that they train on a lot of data. But in general, influence-aware models might lie anywhere on the spectrum, where on one side you have super data-driven methods like conditional behavior prediction or CBP, or on the other side you might have super structured models from something like game theory. And there's also some other models on the spectrum, like latent intent models for playing games with people, or discrete versions of this latent intent model. But in this work, we introduce a method called model-based conditional behavior prediction that doesn't prescribe as much about the human as a game theoretic model might, but also doesn't require a huge, large pre-existing data set. And specifically, we're interested in extending the CVP idea to scenarios where we don't have these kinds of data sets, like collaborative manufacturing or in-home robotics. So if we go back to our influence-aware safe HRI problem, in this project, we focus on two things. First, we focus on constructing the robot's objective itself. And second, we assume that there's some discrete set of known goals that we're trying to estimate online, instead of having Z be some arbitrary learned representation. So we're thinking about conditional behavior prediction with goal states, where in general, you might want to estimate the human's goal in isolation, meaning you would just predict what the person wants to do based on the history of what they've done so far. But what you might actually want to predict when the person is interacting with someone, or is interacting with a robot, is what they would do while the robot is around. So for example, if the robot goes and picks or moves to goal Z1, the person might react to this and say, okay, I actually want to go to Z2 instead. So the key insight in this work is to separate inference of this prior goal and the posterior goal, where a lot of work in HRI has focused on doing what we call observational goal prediction, or just predicting based on the history that you've seen so far. But in this work, we introduced this additional conditioning on the future goal of the robot to get a model of what the human wants to do, conditional on what the robot wants to do. And we study this in a simulated manufacturing setting, where the human state here is in blue, the robot state is in red, and potential goal states are in green. And in this work, we recognize that having this influence-aware prediction model actually gives us some freedom to choose the robot's objective automatically. So we utilize the CBP model to switch between what we call courtesy and influence objectives, basically thinking about, okay, if I want to stay courteous around the person, that means that I want to let the person do what they want to do. And you can like model that very easily using a conditional behavior prediction model. But on the other side, you might sometimes actually want to influence the person to become more efficient. So change what the human ends up wanting to do so that you're more efficient in this team. And so we automatically switch between these two objectives. This goal that the two objectives pick are pushed into our safe controller, which I won't really get into here. But ultimately, this gives you a robot action, and this controller together is our influence-aware controller in this work. And I'll also note that this is not super typical of CVP approaches because they typically assume that the robot's objective is fixed, and just make the robot aware of the low-level influence it has on the human's actions, but not necessarily the high-level influence they have on humans' goals. So we ran a bunch of simulations comparing our influence-aware model to two different baselines. One is a naive goal selection algorithm that the robot always picks the same goal and doesn't change. And the other is a reactive baseline where the robot waits to see what the person is going to choose and then choose something else in response. And here we're measuring metrics on the axes of courtesy and efficiency. So courtesy means how often are you actually changing the simulated human's mind. And you can see that our influence-aware model changes the human's mind the least. And we can similarly measure efficiency metrics in terms of how many goals did the two agents select in this domain. And you can see that on average, our influence-aware model does pretty well, but the two baselines each are good at interacting with one kind of human, but bad at interacting with the other kind of human. So a naive robot is very good at interacting with this uncertain human in the middle, where the human is similarly waiting to see what the robot's going to do, and then reacts in turn, versus the reactive robot is very good at interacting with a stubborn human that similarly always chooses the same goal and doesn't change over time. We also wanted to see if this holds with real people, so we ran a user study with 21 participants to compare these three controllers and see if our conditional behavior prediction model actually helps. So here we can see an example of real users being influenced towards efficiency. In these plots, the human is always the blue dot, the goals are these little X's, and the robots are the different colored other dots. So you can see an example of the same user interacting with all three of our algorithms. With the naive robot, they're like not really sure what to do before they pick this faraway goal. And with the reactive robot, sort of both agents aren't really sure what to do before the human picks this faraway goal again. But our influence-aware robot actually realizes that the person might be hesitating, so it picks this faraway goal to influence them to choose this very close goal. And you can see in the same amount of time, the two agents are actually able to get much farther into this interaction. And the other cool thing we saw in this study was that the influence-aware controller automatically switched its objective based on the kind of person that it was interacting with. So on the left, there's one user that doesn't really know what to do. So the robot successfully influences them to choose this very close goal to themselves. And on the right, you can see a video of the robot trying to do the same thing, but realizes halfway through, okay, this person's not going to change their mind, so I'll just be courteous and choose this goal close to me, and then continue on. And you can see this play out in the overall results of the study. People tended to score less and hesitate more with the reactive robot, while they do pretty similarly with the naive and influence-aware robots. You might notice that the naive robot actually did the best in terms of goal selection with people. And this is really because people were okay to be followers in this interaction, but they weren't necessarily happy about it. So we asked a bunch of subjective questions about their interactions with the robots. And we ask them basically Likert scale questions where 1 means they strongly disagree, 5 means they strongly agree, and they're given a bunch of statements to rank whether they agree or disagree with them. You can see that on the question of whether they thought the robot accounted for the goal that they wanted to pick, they disagree, say the naive robot did not account for their goal versus the reactive and influence-aware robots did account for this. They also say that they think that the naive robot actually changed the goal that they originally wanted, versus the reactive and influence-aware ones, which did not tend to change the goals that they actually wanted. And then we asked the people to rank, like which was your most preferred robot to interact with. And the plurality of people said that the influence-aware robot was their preferred method. And as a fun fact, if you treat these rankings as like choices in an election, you can run a ranked choice voting algorithm, and our influence-aware robot does win that fake election. Yeah, so now I'll talk about my last project, where I'm thinking about sort of the full scope of influence-aware safety together. So going back to this problem formulation, again, we have this problem where we want to stay safe around the person while understanding how their intention is affected by the robot's future controls. So in this setup, it's a similar simulated collaborative manipulation environment where the robot is going to be on the left, the human is still a simulated human in the right, and the goal for both agents is to choose one of these four objects on the table without colliding with each other, and the objects are known a priori to both of the agents. So if you're naive and you think that you can always influence the human, this might actually result in some collisions. So say the robot thinks that it can change the person's mind from choosing this green mug. This may result in a collision. And this means that the robot stays live, which is the green check mark at the bottom right, meaning that it reached its goal, but it's actually not safe because it resulted in a collision. Um, on the other hand, you might naively try to stay safe so that you don't collide with the person, but this may result in compromising the robot's performance because it can't actually reach its goal because it's ultimately not aggressive enough in trying to change the human's mind. So the key idea in this work is to explicitly include a model of the robot's influence on the human's actions to allow the robot to safely influence the person. So we introduce our method called SLIDE, which stands for Safely Leveraging Influence in Dynamic Environments, and see that the robot automatically learns to influence the person's goal selection, and when it's able to influence the person, and when it's not able to influence the person, it chooses like safe backup actions shown in this case. So now I'll step through a little bit about how we actually solved for a policy like this. It's formulated as a reach-avoid dynamic game using Hamilton-Jacobi reachability analysis, where the overall goal is for the robot to solve for a safe policy that optimizes this value function, where the robot is treated as your ego agent and a simulated human is treated as the adversary that's trying to collide. And this value function is actually the same value function that I was talking about at the beginning. It just now is formulated slightly differently and encodes both safety and liveness constraints, meaning you want to both avoid collisions but also reach your goals. And the first thing we do that's a modification from the standard reachability analysis is to do analysis with an extended state that includes both the physical state of the system and the robot's belief about the human. So this is done to enable the robot to proactively understand how its belief would change during this interaction, perhaps by gathering information about the human's intention. And this belief is constructed by querying a predictor that takes in a history of both agents' actions, as well as the robot's future plan. So this is, again, a conditional behavior prediction model. And then this predicts the human's future trajectories. And these predicted trajectories actually construct the belief state directly. The problem also takes a set of failure states to avoid, which are defined by this g of x, which is called the failure margin function. In this case, the set of failure states is like just collisions with each other. So you want to make sure that the robot is not colliding with the person. It also takes a target margin function, which defines the target set of states, defined by this L of x. And in this case, the target set is just the robot reaching these any of these four goals in the scene. Yeah, the other important piece of this problem is how the adversary or the human is allowed to act during the training. So we restrict the set of fully dynamically feasible controls to be realistic controls given our prediction model. So let's take a case where, say, our belief gives us these three different trajectories that we think are likely for the human to take. First, we'll look at the probability of each of these modes, then look at which of them are greater than 5% probability. This is basically just a hyperparameter, and filter those out. So we'll consider only these modes that are greater than 5% probability in the space of human controls, look at the one standard deviation bound for each of these modes, and then allow the simulated human to take any action in this big set of possible controls. But what's important is that this set is smaller than the set of fully dynamically feasible actions, which means we're not thinking about a worst case adversarial human, but only a worst case human that is restricted by our prediction model of them. To actually solve this problem, we use adversarial reinforcement learning, where the robot's policy and a simulated human policy are trained alongside each other, so that you can be robust to sort of whatever potential human you might interact with in the future, given the assumption that they're acting according to your prediction model. So the full pipeline looks like this, where you have some specification of the target set, failure set, and your prediction model. You train the policy offline, or it's using online reinforcement learning, but offline from your actual interactions. And then online, you'll take the trained policy and interact with a human that is doing some kind of goal-reaching policy. It could be real humans. In this case, we haven't actually deployed with real humans, so it's all still in simulation, but the human model that the robot interacts with online is different than the one that it trained with adversarially. So we find that compared to a standard robust approach that doesn't include this influence-aware prediction model, our slide policy influences the human to choose a different goal so that it's more efficient for the team. And you can see this on the bottom plot, where this is showing what the human's goal was over time in these two different interactions. On the left, you can see that the human chooses this yellow bug, which it changes to at about 1.2 seconds, versus on the right, the human model never changes its goal when interacting with the robust policy, which means that the robust policy actually takes longer to reach its own goal. So quantitatively, we find that the slide policy has the highest completion rate and faster completion times without becoming significantly less safe than all of our baselines. The baselines here were a pure goal-reaching controller, which is called no safety here, a simple safe controller called SSA basic, where it doesn't try to reach its goal at all. It just tries to avoid collisions. A robust reach avoid controller that contains no belief state, like I was showing on the previous slide. And the closest baseline is this marginal reach avoid controller that does have a belief state and a prediction model. It just does not include the influence-aware prediction. So it doesn't think about how the human's goal will change as a function of the robot's future plan. So the question we wanted to answer is, why is the slide policy significantly more efficient at completing its task? And so we looked at the sort of structure of the conditional behavior prediction model. So here you can see that there are different robot plans visualized in the different colors and the different most likely predictions of what the human wants to do in the corresponding colors. And you can see that given each robot plan, it's actually quite different on what we think the human is going to do in response. And this is sort of a not possible if you don't have a conditional model. And so we think that this is sort of the reason that we're able to become more efficient. And to make that more concrete, we look at some metrics on the prediction model themselves, comparing our CBP model to a marginal prediction model, which again is not conditioning on the robot plan. And you see that on average and final displacement error, the average displacement error is about the same for the two models, but the final displacement error is pretty much lower across the board for the CBP model. And more specifically, this inferred control bound that's constructed using the prediction model is actually smaller across the board for the slide policy, which means that it's able to exploit this influence to take less conservative actions when interacting with a person. And finally, we test the slide policy against a stubborn human that never changes its mind, which was not explicitly in the training data for the CBP model, but we find that it's actually still robust to this behavior because of the construction of the human's control bounds, so it's not blindly trusting the CBP model, and it still ultimately finds a safe alternative goal, even though it tried to influence the person to change upfront. Okay, so zooming out a bit again, this is sort of the framework that I've been talking about for all of my projects, and I really think that this is a pretty general framework for learning interactive and safe robot policies. And I think the key pieces of this are the human's intent dynamics and their dependence on the robot's controls, and having a safety constraint in the real world, meaning that you still want the person to be safe in some physical way. And like I mentioned at the beginning, thinking about motivation from AI systems, I think this is actually super applicable to a broader set of problems than what I've talked about in this work, where you can still consider for example, a language model interacting with a person as a very underactuated system where the robot or the language model can take language actions or utterance actions. But you still want to think about what the person is going to be doing in the physical world and have that be your safety constraint, and still think about the robot's influence over the person and trying to keep them safe in this way. Yeah, so that's basically it for my talk. I just wanted to say thank you to all of my collaborators on the papers I've talked about today, as well as my lab mates in the Intelligent Control Lab and Intent Robotics Lab, as well as some funding sources. Yeah, thank you so much.
Thank you so much, Ravi. That was super, super insightful. I've followed your work in safety. I think especially the influence-aware modeling is a little bit new. So um, yeah, thanks for sharing that.
Yeah, of
Great.
course.
All right, so I think we'll open it up for questions now. So folks, if any of you have questions, feel free to unmute and ask Ravi any questions about all the work that he shared here. I could maybe kick things off. I had a question about especially the auto distribution scenario you had in your most recent work.
Mhm.
So were there cases where when you were trying to induce these OOD policies, OOD behavior, did you have some unsafe actions that the robot took, or something that kind of surprised you in the way the robot behaved in these stubborn scenarios?
Yeah, so there were definitely some cases. I think it was not super prominent in this like stubborn human scenario, but definitely there were cases where you would get like very, very close to colliding before it decided, okay, actually I need to back off a little bit. I think it was actually more surprising that it still was able to stay safe in a lot of those cases because we weren't explicitly training it with that. So I think this was really a function of the way that we constructed our problem to be a little more robust than like sort of the basic understanding of using a prediction model. We did also have a little bit more ablations in the paper where we were testing with sort of an adversarial goal selection where the human always chooses the exact same goal that the robot is choosing. And in those cases, you do see that the robot ends up breaking down a little bit and can't stay safe all the time, though it's still like reasonably good. But yeah, I think there are always bounds of where like you haven't trained against this kind of policy, so things will break down. But I think it was very cool to see that it was still able to like generally stay robust to like slightly out of distribution scenarios.
That's pretty impressive. Yeah. Cool. Any other questions from folks online? You could also drop stuff in the chat if that would be easier. Um, I guess I'll have another one, which is when it comes to using belief space as you're kind of working with like high dimensional problems. Do you
Mhm.
have any insight into how to kind of make sure that that stays tractable um, when you're, yeah, especially as like the number of dimensions kind of explodes?
Yeah, it's a great question. So, like, really, a lot of safe control work has been limited to regimes where you have pretty low dimensional systems. For this reason, like, you need to do stuff like discretize your state space, or you want to like make guarantees about the kinds of systems that you can stabilize or stay safe, given like a written down dynamical system. Really, so the reason that this worked out in this project actually for a reasonably high dimensional system was because we were just throwing it all into some reinforcement learning. It is still like motivated and formulated as a safety problem, so it's not like vanilla reinforcement learning. But yeah, we were able to do this with like about a 40-dimensional state space for the human robot system, including the belief dynamics. So I think it's a great sign that like these reinforcement learning techniques are able to like scale reasonably well to this kind of environment. There's been some work also from other students in Andrea's lab that have looked at even higher dimensional systems than 40-dimensional, thinking about like doing safety analysis in the latent space of a world model, and that gets even more complicated. I think the question is less to me about whether you can scale to this kind of system, because like learning-based techniques can help you scale to like almost arbitrarily high dimensional systems, is really about like the kinds of guarantees or the kinds of uh like the safe behaviors you can get out of doing learning in that sort of high dimensional space. And I think the promising directions to me are doing some things like you could explicitly think about what does it mean to have uncertainty in your like high dimensional state space or your belief space, or do like post hoc analysis, like given this learn policy, can I do something like neural verification or conformal prediction to say what are the bounds of what my learn policy can do, and try to make sure that you're deploying them in those kinds of regimes. Yeah, I think the basic answer is like it's becoming more and more feasible to pose like safety problems using modern like learning based techniques. But yeah, the question then is like, what do you do about the guarantees that you wanted to start with? And I think that's still definitely open research right now.
Excellent. Thank you.
I don't know if this makes sense as a question, but I've been trying to model implicit goals, and I wonder how um, implicit preferences in terms of safety can be modeled in, and how you about those. Like,
Hmm.
because each one can have like some different safety implicit constraints,
Mm.
and how do you model those differences across all the possible human models with different possible safety constraints?
Yeah, yeah, that's a good question. I think like in one sense it's n not necessarily hard to say that you have some implicit model of the human's preferences inside this formulation where you're just saying, okay, I have this like variable that represents the intent of the person and I want to simulate how that evolves over time. If you have a good enough simulator, which I guess is sort of part of the problem oftentimes is like being able to simulate how people's preferences change. And I think, obviously that could be done through like data-driven approaches, but yeah, you want to be able to verify that that kind of simulation is realistic or reasonable for a suite of real people. Yeah, I think there's also interesting questions on what it like is safety necessarily defined across people, or is it sort of like user dependent? And that I think is also important direction for people to study. Like, can you learn what an individual person thinks is going to be safe for a robot to do around them? Like maybe I have a much larger personal bubble than the average person, and I don't want my like household robots to be staying that close to me. And I think you end up needing to do a lot of like either personalization during interactions like online learning, or you need to collect a lot of data on like what are the different modes that people in general have on these sorts of preferences. And I think there's a lot of cool work in thinking about like representation alignment or preference learning from people that you could use for that kind of thing. And yeah, I think it certainly is important, and I don't have a great answer for how you could do it, but I think there's a lot of different like avenues you could take to start looking at that, answering those kinds of questions.
Yeah, it goes a bit beyond what you have presented. I'm aware of that. I
Yeah.
just was trying to connect with something more familiar to me.
Mm. Yeah, yeah. No, I think that makes sense. I think like thinking about um, sort of implicit influence and implicit like preferences in the world is definitely super interesting directions.
And I have a general question that
Sure.
Yes.
probably, like especially for folks who are kind of new to HRI and then influence-based like behavior, um,
Hmm.
could help understand. And this is something I've had a doubt about as well. So when you have these plans that the robot is kind of executing, how do you delineate, like more formally, um, uh, whether the robot's plan ended up influencing what the human is doing? Um, is there kind of a cue that you take into account as you're doing these studies, or something else that we, as people who are interested in the space, should account for?
Yeah, so it's definitely very hard to do this like in deployment with real people online. I think because the question is like I only get to observe what the person actually did, right? Like I don't get to know what was in their head to begin with and whether that changed. So what's happened in a lot of my work is I have like models of people and how their goals might change or how their intentions might change. And then it's, because I've defined the model in simulation, I see what is the point in time where the like true plan that it took deviated from its initial, the like simulation of the initial plan. But I think there's other work that's thinking about how you could do this sort of distributionally, where you have data sets of people's behavior, and you can see like you can basically measure what do people do on average in this situation when you're not accounting for like robots in the scene versus what happens on average or for a particular agent when you do account for robots on the scene, and see if those distributions are different, and basically say that if the like conditional distribution of behavior given a robot in the scene is different than the sort of marginal distribution of what the person would have done regardless, then like influence is present. But I totally agree that it's very hard to measure for like online real world interactions. And I think there's definitely certainly there would be some cues that you could look at for like physical interactions like the reaction time or like hesitation, stuff like that. But it's not been too much of a focus of my work to this point. Yeah.
We have another question.
Hello.
Hi, we can hear you.
Yeah, you mentioned like in your first experiments where the user and the robot had to reach a goal. You said that users had preference for the robot that influences their behavior. I would like to understand like if you have an explanation for that, because to me it seems a bit counterintuitive. Like in general, people will like the robot that let them do what they have to do first, instead of liking the robot that influence their behavior. Do you have an explanation for that?
Yeah, that's a very good point. So I think in the work that I have done so far, it has been in situations where people don't actually have super strong preferences for how they're going to be doing the task, which is why it's like okay to be influenced by a robot. So it's sort of been motivated by things like, maybe you're collaborating with a robot that's going to help you clean your house. Like I don't have super strong preferences for the order in which I'm going to pick up objects. I just want the whole thing to be clean. And in that case, it's like pretty easy to imagine that I'm okay with the robot choosing to do something and I get to do something that actually like maybe I wouldn't have thought about beforehand. And so if you ask people like after the fact, like because they didn't have like super strong preferences up front, I think it's like they're perfectly happy to be influenced by the robot's decisions. I think in other cases where you're thinking about like I have a very strong preference for like I want my dishes to be organized this way. The robot influencing me is going to make me pretty unhappy. And so I think that's definitely an important factor to consider in like more general scenarios. I think the pitch from my side is just that you want to do this purposefully instead of accidentally. Like you want to influence people in a way that you understand, which is why part of the work in that one project was about switching between being influential and courteous. So if you find that the person is not actually changing their behavior, the robot should not like keep pushing and like try to influence them unless it seems like they're okay with it.
Okay. Thank you.
Yeah.
Sweet. All right. Just so that we're respectful of everyone's time, I think. Thank you so much again, Ravi. This was super insightful.
Thank you.
Bye. Thanks a lot.
Thank you. Goodbye.